Okay, we're going to continue on with probability in chapter 2. So this is from section 2. So we're going to learn some probability rules, such as the addition rule. So things that you'll be asked is things like, what is a sample space? And a sample space is the set of all possible outcomes. So it helps sometimes to list them if there's not too many. So for example, if I flip a coin twice, the sample space is I could get heads, 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 tails, tails, heads, tails, tails. So if I wanted to know what's the probability of getting heads heads two times in a row, I know my probability is 1 out of 4. Another way to create this is you could do a tree diagram. So in my first toss, I could get heads or tails. And then in my second toss, even if I flip heads first, I could still get heads or tails second if I flip tails. So that's how this is created. So this is heads, 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 tails, tails, heads, tails, tails. So that is how you can create a sample space with a tree diagram. So if I wanted to do 3 tosses, I would have 2 more branches off of each of those. So 2 branches off of each of these, then I would have 8 possible outcomes for flipping a coin 3 times. So the probability model shows the sample space and the probability for each outcome. So for example, I'm going to have the event be the number of heads. So I can get, if I flip it twice, I can get no heads, I can get 1 head, or I can get 2 heads. So I have to list all the possible outcomes. And then what's the probability? So each one of these had a 1/4. So the fact that the 1/4 added together gives us 1/2. So notice that the probabilities should add up to 1 whole. So everything should be represented. And then what's an event? It's the outcomes from a chance process. So it's a subset of the sample space. And usually we call it like event A, we would use a capital letter. So if you see it, and you're going to see it later on in the notes. So imagine flipping a coin 3 times. What are the possible outcomes? So I am going to go ahead and quickly put in my 2 more little branches up here. So if I follow my branches, I could get heads, heads, heads. I could get heads, heads, tails. I could get heads, tails, heads. And I could get heads, tails, tails. And then I've done all I can there, so now I'm going to go to this one. Tails, heads, heads. Tails, heads, tails. Tails, tails, heads. Tails, tails, tails. So I just follow the branches, and if I can try to think it out this way too, but I don't jump around. There is a process that I don't skip everything. So describe the model and use it to find the probability of getting at least 1 head in 3 flips. So first of all, this is my sample space. So again, if I'm flipping it 3 times, what are the possible outcomes? If I'm looking for the number of heads, it's possible that I'd get 0 heads out of the 3. I could get 1 head out of the 3 tosses. I could get 2, or all 3 could be heads. So now those are my possibilities. So again, this is now out of 8. So the probability of getting 0 heads is only this one. So that is, and you can answer as a fraction or a decimal. So I could put 1 out of 8. Or if I divided that, that would be 1.125. And then up here would be the same thing. 3 heads only occurs this one way, so 1 out of 8, or 0.125. And then 1 head occurs, so 1 head occurs here, here, and here, so it occurs 3 out of 8. And then I believe 2 heads would also occur 3 out of 8. And if those decimals are 0.375, 0.375. So again, this adds up to 1.0, or this adds up to 8 out of 8, or 1 whole. So you can You can show your probabilities as decimals or fractions. So now I'm going to answer the question, what is the probability of getting at least one head in 3 flips? So again, when I say get in the habit of showing your work, I'm going to write what's the probability of at least one heads. So again, that P stands for probability, and then I am putting the event here. So I didn't call it a capital letter. I could have said that what it was, but I could also write out what the event is. So what's the probability of getting at least one head when I flip a coin 3 times? And now I can just use my table. So at least one head represents these 3. So I can just add up 0.375 plus 0.375 plus 0.125, and that gives me a total of 0.875. Or if you noticed, what's something that could be easier than adding up 3? So there's something that I want you to pay attention to that we're going to actually want to use a lot in this course. When it says the probability of at least 1, that's the same as 1 minus the probability of none. Later on, this won't be a nice discrete table. It'll be continuous, where we're going to be using the normal CDF. So if I had something that was 20 across instead of just 4, I wouldn't want to add up 19 possible percentages and have to find each of those 19 percentages. It's easier for me to find the probability of none and then find the complement, because at least 1 is the same as the complement 1 minus the probability of getting none. So I could have just done 1 minus 0.125 and gotten my same answer a little bit quicker, actually. So again, when it says, so don't, if you just do this on your calculator and write down this number, you will not get credit for it. You're expected to show how you got that answer. Even if you think it's obvious, write it down to get full credit. So we've got 5 basic rules that are talked about already. So the probability of any event has to be between 0 impossible and 1 guaranteed. If S is the sample space in the probability model, all the probabilities should add up to 1. Everything should be represented. And then this is the probability of an event A is the number of successes of the event over the total number of possible outcomes. This denominator is how many things would be in your sample space, and the numerator is how many of those possibles were successes. So the probability of not A is simply the complement of the probability of A. So again, an event happens or it doesn't. So complementary. You might also see it look like this. So probability of A would be the event, and then this little C is the complement of A. So it's just subtracting from 1. And then there's mutually exclusive or disjoint. Those 2 phrases are used interchangeably. So if 2 events have no outcomes in common, then the probability that one or the other occurs is the sum of their individual probabilities. So the addition rule for mutually exclusive events, they have nothing in common. If I want to know the probability of one or another event happening, I just find their probabilities and add them together. But they have to be mutually exclusive, because if they're not mutually exclusive, I'm going to get a number bigger than 1 or bigger than 100%, because a couple things are going to be in both events and we'd be adding it twice. So to be mutually exclusive simply means no outcomes in common, so they could never occur together. For example, rolling an odd number and rolling an even number are mutually exclusive. I can't roll a die and have a number be odd and even at the same time. But however, if I say rolling an even number and a prime number are not mutually exclusive, because 2 is an even number and it's a prime number. So if I said the probability of odd, that happens 3 out of 6 times. Probability of even also occurs 3 out of 6 times. So if I add, so what's the probability of odd or even? Again, or is telling me it's a the addition rule. And is a multiplication rule. So 3, 6 plus 3, 6 is 6, 6 or 1 whole, which should happen because I can only roll an even or an odd. But if I say rolling an even number, that's, again, 3 out of 6. And then the prime numbers on the die are 2, 3, and 5. The thing is, that's also 3 out of 6, but that is 1 whole already, and I didn't include 1 in my roll at all, so it shouldn't add up to 1 because I'm missing the probability of a 1 is 1 out of 6. So if I say probability of odd and probability of prime, if I add those two numbers together, I'm already at 1, which means that I'm rolling a 1 couldn't even happen. So it doesn't include. So that would be a problem. Okay, so let's look at an example. So randomly select a student who took the 2010 AP Stats exam and record the student's score. Here's the probability model. So again, these are all the possibilities. You can score anywhere from a 1 to a 5 on the AP exam, and it shows the probabilities of getting those scores for that year. So how do you show me that this is a legitimate model? There's 2 components. Number 1, each probability is between 0 and 1. Because if I just add them up and get 1 whole, what if I put a negative probability even though it doesn't exist? If I put a negative probability in there, I could get some negatives and positives and still add up to 1 whole, but my probabilities also have to be between 0 and 1. So each probability is from 0 to 1, or is between 0 and 1. So that checks off. Everything is between 0 and 1, and the sum of the probabilities equals 1. And again, I should verify that. I shouldn't just assume it. So I'm going to just simply add them up. So 0.233 plus 0.183 plus 0.235 plus 0.224 plus 0.125. I just verified that it does add up to 1 whole. So both components have to be talked about. Okay, so find the probability that a student scored 3 or better. So probability 3 or better. Get in the habit of writing out the probability and write out the event. So the probability of 3 or better, again, is this group right here. So I could just, and again, show the work. Show what you're adding, even though you're going to plug it in the calculator and do it. Show your work. So if you do that up, you're going to get 0.584. So the probability of getting a 3 or better, that means about 58.4% of all students that took it scored a 3 or better on the AP exam that year. Find the probability the student did not get a 1. So again, not a 1, I could add up the probability of 2 plus the probability of 3 plus the probability of 4 plus the probability of 5. I could add up those 4 numbers, but again, the easier thing for me to do is find the complement. So I can also just do 1 minus the probability of getting a 1. So 1 minus 0.233 is so the probability of not getting a 1 is 0.767. Okay, so the general rule for the addition rule, so when they were mutually exclusive, it was just these two. But if they're not mutually exclusive, we have to subtract out the overlap. We have to subtract out what occurs in both events, so we don't add it twice. Is it on the formula sheet that I'll give you next week? Yes, it is. So even though you'll know it, it is on the formula sheet for you. And if the events are mutually exclusive, then they don't have anything in the intersection, the probability would be 0 if they are mutually exclusive. And that's why if this is 0, we're just left with this part of the rule when they are mutually exclusive. Okay, so now we're going to do a two-way table. So what is the relationship between educational achievement and home ownership? They took a random sample of 500 people who participated in the 2000 census. Each member was identified either as a high school graduate or not, and either as a homeowner or not. So overall, 340 were homeowners, 310 were high school graduates, and 221 were both. So I've already got the skeleton of our two-way table here. So a two-way table meaning we got two categories. Again, I could have put these up here and these down there. It doesn't matter. But the two questions were, are you a high school graduate? Are you not? Are you a homeowner or are you not? And then I'm going to have our totals. Okay. So what do I know for sure? I know that 221 were both. So that means they are a high school graduate and a homeowner. So 221 would go there. I also know that the total of the sample was 500. So when I add everything up, I should have a 500 right there. I know that 340 were homeowners. So when I add up my homeowners row, it should be 340. And I know 310 were high school graduates. So when I add up that column, I should get a total of 310. So that's all the information they gave me, but I should be able to work backwards to figure out the missing parts. So if I know that this row's total is 340, how do I find, if I have 340 homeowners and 221 graduated, how many didn't? I just have to subtract. So that gives me 318. Now I can also do this column. So if I have 310 high school graduates, I can subtract out the homeowners, and that tells me how many are not homeowners. And then I also can figure out this total. So this total should add up to 500. So if I do 500 minus 340, I'll get 160. And now again, I can subtract in this row. 160 minus 89 is 71. And then I can add up. Why did I put 318 there? 340 minus 221 was, I put 22, not 221. Okay, hopefully you caught that before I did. So that should have been a 119, 71, again 190. So this row works out, this row works out, this row works out, column, 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 everything makes sense. So I've got everything filled in from what information they gave me. And now I'm going to use the table to answer the question. There's a whole lot of formulas out there for statistics and probability rules. I just use the table. So we choose a member at random, find the probability the member is a high school grad. So probability high school grad. I'm writing out what I'm finding. I'm showing the event. So what's the probability they are a high school graduate? I just have to look up how many were high school graduates. 310 out of 500. You are perfectly fine leaving it as a fraction, or if you wanted to divide it, that would be 0.62 or 62%. High school graduate and owns home. And owns home. So high school graduate and owns home, that was our 221 out of the 500. So that is about 44% or 0.442. what's the probability that they are a high school graduate or owns home? Okay, so how can I do this? So what's the probability that they're a high school graduate or owns a home? So if I do the probability that they're a high school grad plus the probability that they own a home, but some are in both, so I want to subtract out the probability that they're a high school grad and owns home. So I've already found a couple of these. So the probability they're a high school grad we already found was 310 out of 500. The probability that they own a home, there were 340 that owned a home. So notice if I added these up right now, I would get that there are 650 out of 500. So again, that doesn't make sense. I have to subtract out the group that was in both. So the group that was in both was the 221 out of 500. So if I add up my 310 plus my 340 and subtract out my 221, I am left with 429 out of 500. So that is 0.858, so almost 86%. So if I were using the table, what I do sometimes is I just don't add twice. So high school grad or owns a home. So if I did the high school grads, I know that there are 310 high school grads. And then if I do the homeowners, I just specifically would not have, so if I'm looking at this group and this group, I don't want to add this twice. So I could have just added the 221, the 89, and the 119. So with the table, I could have also just made sure that I did not include that 221 twice, and I could have just gotten straight to my 429 out of 500. But if you like to show your work and show that you're using the formula, this is what you would want to write down. But this is perfectly acceptable as well. And that's why the tables are helpful and why I don't really need to know the formula, because I can just look at the numbers on the table to answer my question. Okay, and then the last page, we're also going to do a Venn diagram and a table again. So according to the National Center for Health Statistics in December 2008, 78% of U.S. households had a traditional landline. 80% had cell phones and 60% had both. So we want to select a randomly selected household in December 2008. So again, I'm going to start off by doing a two-way table. And what do I know? So 78% had a traditional landline. So that's the total. I'm going to change these two proportions. So 78% had a landline, so I can fill that in. 80% had cell phones. That's, again, our total. And then what else do I know? I know that 60% had both a cell phone and a landline. So I can put my 0.60 right there. So again, I can figure out in this row what's missing. If I subtract these two, what's missing is 0.18. I can figure out what's missing here. That would be 0.20. And then where do I go from here? Well, what should the table total be? So since these are percentages, it should add up to 100% or 1. So again, I can figure out what's missing here is 0.22. And then I can figure out what's missing in this row, 0.02. And then I can add up my total and get, or even this. So again, this adds up to 100%. So that's what a two-way table looks like. a Venn diagram, and here's what we're talking about with the events being capital letters. So I can call this circle A, those are landline, and B is cell phone. So if I assign them, then later on I can just say the probability of A and I don't have to write out all the words every time. So if I were doing a Venn diagram for this same problem, I always start with the intersection. So I would have started with 60% have both. And then I would go with 78 had a landline. Now, this is what mistakes people make. They put 78% in there. Well, if you think about 60% is already in the circle, so we now have more than 100%. So that doesn't make sense. The whole circle should add up to 78%. So that means that this part would have to be 0.18. Now I have 78% in that circle alone. Same thing with the cell phones. 80% had cell phones, 60% are already in there. So that leaves 20% outside. And I know the entire thing should add up to 1. So if I add up what I have so far, I have 80. This only adds up to 98%. So that leaves 2% that aren't in either circle. So this still adds up to 100%. So you can create a two-way table, or you can create a Venn diagram, and then that helps answer the questions. So if A is a landline and B is a cell phone, I can now just use A and B. I can still write out the words if I want to, though. So find the probability that they have at least, but I'm going to write it out, at least one of the two types. Now, if you remember what I said earlier, the probability of at least one is the same as the complement of 1 minus the probability of none of the phones. And you'll see that it's actually easier. So none was the 0.02, so 1 minus 0.02. So there is a 98% chance that a household has at least a cell phone or a landline. So at least one of the two types. If I use the formula, it's the probability of A plus the probability of B minus the probability of the intersection. So if I did probability of A, 0.78, plus the probability of B, 0.80, and subtracted the intersection, which was 60, that also gives me my 0.98. So again, you can do it either way, but in the future, we're going to definitely want to do 1 minus the probability of none in the future. So it wouldn't be a bad idea to get in the habit now, even though you don't have to. You can certainly add up 3 numbers just pretty quickly. Okay, so find the probability that, if I thought this through, I'd probably switch them. So I would have done D before I did C. So find the probability that they have neither type of phone. Again, as far as showing my work, if I have drawn a Venn diagram or shown a table, you don't have to show me the mathematics there because you've already shown me by creating your Venn diagram. So I can see it right here that you could, and you had to figure that out. That wasn't given. So you actually showed a lot of your work just by creating a table or the Venn diagram. And then find the probability that the household has a cell phone only. So that's the probability of only a cell phone. And this is where the Venn diagram helps. The probability of only having a cell phone is this right here, and that would be 0.20. That's where I actually prefer the Venn diagram to the table to see what's in what. So cell phone only is 0.20. And again, just reminding you, using the fact when I see the word at least one, it's the complement is none. And that wraps up our examples for 5.2.